All right, so this is the second part of section 10.2, ellipses. We'll do an example here, but the main part of this is talking about eccentricity, and it's about the measure of how stretched out or how round an ellipse is. But let's start with number 8. All right, an ellipse has foci at -1 plus or minus the square root of 18, comma 9, so that's the location of the two foci. The distance from the edge of the major axis to the nearest or closest focus point is the square root of 2 units. Write the equation of the ellipse. So remember, in order to write the equation of the ellipse, we need to know where the center is, right? We need to know center. We need to know, we also need to know where, what A is, what B is, and then we really need to know the orientation. So how is it oriented? So figure out these things, and then once you know those, you can write the equation. Okay, so if we think about this, we can look at where the foci are. Remember, the foci is first of all, it's on the major axis, right? So are these 2 points, are these two foci next to each other or above each other? And so we're adding and subtracting to the x, so they're next to each other. So the major axis is horizontal, so that tells us the orientation. Also, remember, the foci are C away from the center. So if we think about how they wrote this out, they gave us a lot of information here. We can tell that the center from this stuff here, we know that the center is located at -1, comma -9 because they've added C to the x, to the y, the x or y coordinate, in this case the x coordinate, or h. So we know this is h and we know this is k. That also tells us what? This tells us that C equals the square root of 18. Okay. So we need to be able to figure out A and B though. Okay, so we know the center, we took care of that, we know the orientation, we need to find A and B. So I know that if we think about maybe drawing a picture of this thing, here's the major axis, here's the minor axis. So we know, and I don't know, I'm not really drawing it to scale, but this is the square root of 18. We can think of that as 3 square roots of 2. And then they told us that this distance out here is also square root of 2. The distance from the focus to the endpoint of the major axis is another square root of 2. So this is a way of telling us, oh, okay, well, we know what A is. A is 4 square roots of 2. And then, and we know that C is, if we want to think about simplifying that, 3 square roots of 2. So we know A and we know C. We can certainly use those to find our B. So we know that B squared will be equal to A squared minus C squared. And so A squared, well, that's just gonna, if we square A, that's 32. And if we square C, that's 18. So we know B squared will be 14. Okay? So ultimately, I'm not going to try to simplify square root of 14 or anything like that, because really, I mean, I said I wanted A and B, but really I need A squared and B squared. So now we can just write the equation. It's horizontal, so I know my A squared is going down here, so that's 32. B squared is going here, that's 14. I know I have x minus and then h. Actually, that's plus, because it's a -1, so it's the opposite. And then y plus 9 quantity squared. Okay? All right, the eccentricity then. So for an ellipse, so it's just a measure of how round the ellipse is. Some ellipses are very circular. You know, the foci are very close together. Remember, when the foci get close together, it becomes more circular. As they get further away from each other, then it tends to be a little bit more elongated. So for an ellipse, the E value is going to be between 1 and between 0 and 1. So if you think about it, a C is always less than A, but C is always greater than 0 for an ellipse. If C was 0, right? So if these 2 points go in together, right? And so if C was actually 0, that means the 2 foci would be right on top of each other. We would basically have a circle at that point, right? Because if you think about the relationship that A squared is equal to B squared plus C squared, if C was 0, then that we could just eliminate that. Then A and B would be the same. That means the minor axis and the major axis would be identical, and we would call that the radius. Okay, so with C as 0, we got a circle. So technically not an ellipse. So we know that C must be greater than 0, but we also know that A is going to be greater than C. Let's think of it the other way too. Let's say that A and C were the same. So as these points get closer and closer to the end point, the foci get closer and closer to the end point, the minor axis is getting smaller and smaller. And so think about this. If these two things are equal, then B would have to be 0. And in which case we would just really have basically a line. I think we saw that in the Kepler video on YouTube. All right, they talked about the extremes, which would be a circle and which would essentially be a line. All right, so if it's an ellipse, this has to be true. And then if we divide through by A, we get this. So that C over A, which is what we call the eccentricity, that would have to be, for an ellipse, between 0 and 1. Okay, not exclusive in that case. So what's the eccentricity of a circle? Well, we already said for a circle, the C values are 0. And so for a circle, the eccentricity value will be 0. Okay, because C is 0. All right, find the eccentricity E for each of these ellipses. So basically what you're looking for is C over A. All right, so this one, we know that A squared equals 16, B squared equals 8. We know that C squared is the difference of those two, which would be 8. And so C is the square root of 8, which is the same thing as 2 square roots 2. And so now, and of course up here we know that A is equal to 4. So basically we need A and we need C in order to write the eccentricity. So C over A now is equal to 2 square roots of 2 over 4. That reduces to, of course, square root of 2 over 2, which is approximately equal to 0.71. As an exact answer, this would be good, but just to get you an idea, so we know it has to be between 0 and 1, and this one's 0.7, so that's fairly elongated. All right, B. So for this one, we want to put it in the correct form. We want to divide everything by 12, so that gives us an x squared over 2 plus a y squared over 3, and that's equal to 1. So those are a squares and b squared. So this is a squared, that's b squared. And so c squared would be the difference. So c squared is 1. And so, of course, also c equals 1. So c is can only be positive value. Remember, it's a magnitude. So even though we would take the square root and get plus or minus 1, in this context, it would just be 1. And so A would be, let's see, a is the square root of 3. And so what is the c over a for us? That is the 1 over the square root of 3, or square root of 3 over 3. And that's approximately equal to 0.577. Okay? So a little bit more round compared to this one. All right, and then this last one, C. So this is good practice for putting it in a standard form into the elliptical form. So let's deal with the x's and the y's separately. Remember, you're completing the square separately for each variable. First, we want to factor an 3 out of both the x terms, so that gives us x squared plus 2x. Let's leave a space for now. And then we want to factor out a 4 out of the y terms, y squared minus 6y. We'll leave a blank. We're going to add something there. We've moved the 27 over to the other side, so we get negative 27. Okay, so what am I going to add here? Half of this is 1 squared is 1. Remember, its true value is not 1, it's 3. We added 3, so we have to add 3 to this side. Half of this is 3 squared is 9. Remember, we're not adding 9, we're adding 36. Okay, so add those equivalent values to the other side. Okay, so we can factor those and write them as binomials now, squared. So it's 3 times the quantity x plus 1, quantity squared, plus 4 times the quantity y minus 3, quantity squared, equals 12. Often you'll see that this number over here is a multiple of these numbers. Now, it doesn't have to be. You could have fractions at the bottom. So a squared and b squared could be fractions, but often you'll see that this number, it's not necessarily the product of these two, as it is in this case, but these two numbers will be factors of this number. Otherwise, we're going to have fractions. So, I mean, it's possible to have fractions, but often you'll see that it's not. All right, so now we divide through by 12, x plus 1 quantity squared over 4 plus y minus 3 quantity squared over 3 equals 1. Okay, so we know that c is equal to 1 because that's the c squared is this difference, which is 1. Square root of 1 is 1. And then a squared is 4, so a equals 2. So this one's nice. The eccentricity here, a is 1/2. Okay. All right, last example, number 10. The orbit of Mars is an ellipse with the sun at one focus. So we could draw in, something like the sun here, right? These obviously aren't drawn to scale. Mars compared to the sun, I mean, I don't know, it's probably 100 times smaller, but we really want to just think of these as points. So when we think about distance, and they're talking about distance between the sun and the Mars, we're going to think of it as a point to point, center to center, not like the surface of Mars to the surface of the sun, but we'll think of distances measured here as from a center of one object to the center of another object. So anyway, all right, the eccentricity of an ellipse, of the ellipse for the elliptical orbit of Mars is 0.0935. So that's pretty round, right? It's pretty circular because that's kind of low. Although Mars, as far as planets go, Mars is fairly circular. I mean, it's fairly eccentric compared to other ones. So a lot of the planets' orbits are very roundish, and that's why for centuries physicists and astronomers, people that looked up at the stars, thought that the planets orbits were circular because they just didn't know any better, and they weren't that far off. They were a little off, but they didn't understand why. And so, you know, as we saw in the video on Kepler, he's one that determined that Mars is fairly eccentric compared to other planet paths, but even it is fairly round because the eccentricity is pretty low. Not like these values up here, right? These are pretty high. All of these were pretty high. This is pretty low. So it's still fairly circular. Okay, the closest distance that Mars comes to the Sun, and again, we're doing center to center, is 128.5 million miles. Find the maximum distance Mars is from the Sun. So because it's an ellipse, right, there are some times when it's closer, the other times when Mars is further away. So again, we're going to talk about this as being center to center. So we know that distance is what they gave us. All right, and so they want us to find that distance. That is what we're looking for. And again, we're assuming center to center. All right, so besides this distance that they gave us, they also told us that C over A equals 0.0935. And, you know, we could take that and rearrange it. C is equal to 0.0935 times A. All right. But we also know that this distance corresponds to what in terms of A's and C's? It's not A, because A would be from the center out. It's A take away C. That little distance in here is C. It's from the center to the center of the Sun. That is C. So we could think about A plus, let's think of it as 128.5 plus C would have to equal A. And so we have two equations here that we can solve for simultaneously. Let's see, let's take out the C and just put in the A, I guess. Maybe that would work well. So that's 128.5 plus 0.0935A equals A. Okay, so now we just solve this for A, right? Move this to the other side, so we get 128.5 equals, and we subtract this from both sides, something like 0.9065A. And then, of course, we just divide both sides by this coefficient, and that gives us an A value of 141.8, and this is in millions of miles, right? We're dealing with millions of miles there. And so that's what A is. And so now what we want to figure out is, okay, what's this distance, right? And so now that distance, that question mark up here, well, that's just A, right? The distance from the center of the ellipse to this endpoint, plus C. So now we want to look at A plus C to find that distance, the furthest away distance that we have. And so then that's just going to be the one, oh, that's not 144, that's 141. All right, so 141.8 plus our C, which, did we find C? Okay, so we didn't find C yet, but now we can, now that we have our A, we just plug that back in. So if we take this, plug that back in up there, we know that C ends up being 13.3 million miles. All right, so we know C by plugging A back into, well, either equation, really. All right, so we know C, that's 13.3 million miles. And now if we add that up, we get 155.5 0.1 million miles. Okay, so that's the furthest away it is. You know, so it oscillates between being this close at some points of its rotation around the sun and this far away when it's on its furthest away from the sun. All right, your homework is listed down here.